study on it. So this group did a good job of highlighting this. So number one, what is that thing up there in step number one?
The virus.
It says free virus. Which virus is it?
HIV.
The HIV virus, or AIDS virus, or human immunodeficiency virus. So that's the HIV guy. Looking at number two, can you tell me what's happening in step two?
It's attaching.
Yes, attachment entry. Good, I read that. But can you tell me what that means in English? Attachment. What is it attaching to? The host cell, this cell. What cell is this? It's our cell, our body cell. Which body cell is that one there?
T lymphocyte.
T lymphocyte. Which T cell?
Cytotoxic.
No. Helper T cell. There's the answer. That is a helper T cell. That gray ball, that is the helper T cell. So in step two, the virus is connecting to the helper T cell, abbreviated as a CD4. So that's your helper T cell. Remind me again what helper T cells do. They activate, command, generals. Those are the ones we talked about. Step 5 last week, right? So the virus is coming in, sticks to the helper T cell. What's happening in step 3? What's it doing to the helper T cell in step 3?
Penetration.
Penetration. What's it penetrating? Cell. So it's sticking its genetics inside the cell. So step 4, the group just talked about. You remember what they told you? Step 4, the virus has to convert itself from viral instruction, which is RNA, to human instruction, which is DNA. Remember that from Biology 112. You're DNA, they're not. So for that to work, you have to convert yourself from one language to another, and that's called reverse transcription, because you're going backwards to a biologist. So the virus is floating around, finds your helper T cell, sticks itself in there, and converts itself into human language. With me so far? Okay, read step 5 and tell me what it's doing in step 5. Inserting itself where? To our DNA. So you and the virus have been assimilated. You're now one. Resistance is futile. Right? So you and the virus are now one piece. Right? No one ever gets that reference anymore. Number 6. What's happening? Yes?
I got it.
Good. Good. Someone got it. Right. Step 6. What's happening in step 6? Transcription. Good. I read that. Can you tell me from Biology 112 what transcription means? You should know that. You have to pass that word to pass that class. 5 credits.
DNA and mRNA.
That's right. It turns on protein synthesis, right? So the virus is making proteins because the virus is now running your cells because you and the virus are one thing, right? So it's not you anymore, it's the virus. What do those proteins do? 8, 9, and 10. What are those things in 8, 9, and 10?
Making of new HIV viruses.
New HIV viruses, baby viruses, new HIV. So in step 6, the virus turns on and basically makes babies, right? You know, realize they're not babies, right? But you get the gist. So these are new HIV particles, right? So the cell is taken over by the virus. The virus orders your cell to make babies, and you crank out babies. So when you get to step 10, what's going to happen next?
They can now go and make babies.
Go back to step 1 and do it again, right? So every time you make baby viruses, then go back and repeat the steps in another helper T cell. So you float around, grab a helper T cell, stick in your genetics, tell that cell to make babies, you make babies, and you repeat ad nauseam, right? Make sense? So that's the basic HIV life cycle. So get out your packet of pain. We're going to walk through some HIV discussion points. And finish up our packet of pain. Find page 29, which looks like this. We're going to do this as a class. We're going to fill in some information here. So find page 29. Someday I'm going to go crazy. All right. So question 1. How does the HIV know that's a helper T cell?
Antigen.
Look at step number 2 on your chart, on those steps. How does it know it's a helper T cell?
Receptor molecules.
Receptor molecules, or the antigens on the helper T. What were antigens again from last week? It's definitely on your final. Markers, shapes, proteins on the surface of cells. So your helper T's have shapes on them. And the virus is looking for that shape. You know the officers in the Army because they wear a different uniform than everybody else. So you know them when you see them. So the virus is looking for those shapes. What are those shapes made out of?
Protein.
Proteins. Antigens are proteins. They are proteinaceous cell receptor. And what does that have to do with genes? From Biology 112, genes code for? Proteins made by your genes, made by your DNA. So your genes make your proteins to make your antigens. That's why they're self. They're yours. So your helper T cells have shapes unique to them that the virus is looking for. Make sense? What cell do we infect? The helper T cell. So you're affecting the helper T cell, the TH cell, CD4 cell. What's this job again for review? Activate the immune cells. Command. Activate. Remember step 5 on down over there? That's what we're going to do. It's to command the immune system, to turn on the immune system. The tacrolimus group had a very good picture of that. Did I even say it right? I can't say it. Yeah, whatever. Okay, so now go to step 8 on your picture, where the baby viruses are budding out. Tell me what happens to your helper T cells when you read step number 8. What do they do? They die! Why do they die? Very good. So if you read step 8, the baby viruses take the cell membrane with them. And what happens when you rip holes in cells? They die. They lyse and die. Just like if I rip this skin off of you. You know that scene in Aliens? Imagine that, right? And to get in real life, there's actually 30,000 babies for every mother virus. So you can tell you that 30,000 things are ripping out your cell membrane. You're going to die. So the helper T cells are going to die off because the virus is killing them as they bud out. Make sense? Which leads us to this. We're going to skip question 3 because I kind of covered that. Let's go down here. Question 4. How long does it take the virus to go from step number 5 to step number 8? Anyone know? They mentioned it actually in their presentation.
24 hours.
No.
2 weeks.
No.
48 hours.
Nope.
A month.
Nope.
10 minutes.
Year, 2 years.
Okay, let me ask you a different question. When you work at the hospital, how often do they tend to go in for an HIV test?
3 months.
Now you understand this step here, 3 to 6 months. Because it takes that long for the virus to make babies that would end up in your bloodstream that you could find on a test. That's why you have to. That's why that 3 to 6 month lag time. It takes about that much for the virus to make babies, right? So that leads us to this one here. What's the difference between HIV and AIDS? Let's go through the wording. HIV negative means what?
You don't have the virus.
No virus. No HIV. You're negative, not present. Rh negative, no blood, right? Okay, smarties. HIV positive means
You have HIV.
you have HIV. You have step number 1 has occurred. Virus is in your body. Step number 1. That's HIV positive. Now, AIDS means
No white cell count.
that's right. You have symptoms of HIV, which we'll get to in a little bit. So HIV is the cause, AIDS is the effect, or the syndrome you get. And there's levels between that. You have ARC and all those kind of fun things. So you can be HIV positive but not yet have AIDS, which means you have the virus hasn't caused symptoms. But if you have symptoms, you had to have the virus first. That's the way that works. Make sense?
Is there a typical trajectory on how long it takes for symptoms to show, or is it different in everyone?
It varies. If you average it out, it's within a year, but that's an average. Some people go their whole, like Magic Johnson's claiming, self-reported, he doesn't have AIDS yet, and he got it, what, in the 80s? Right?
Didn't they just say there's no indication that he even has HIV?
That's the question is, did you even have it to begin with, which everyone claims it did. So the question is, did he go from this and never get to that? Or did he not have this? Or, that's the question. But most people are going to show some kind of symptom, normally beginning in about a year up to at least a decade, within 10 years guaranteed.
With medicine?
No, the medicine is to stop that. If you just left it going. Yeah.
Is there some kind of, or I've heard of some kind of medication that we can give babies that have been exposed to it to kind of prevent it even, and maybe they've had it sort of, I don't really, it was kind of unclear, like if they have it and then actually cures. I know there's not really a cure, but it seems like there's some kind of medication that if a baby's exposed to it, that they can still take it.
But you can do that one there they talked
But
about.
it was like the baby had actually been exposed to HIV.
Right. The problem with babies is they'll seroconvert on their own. So babies will oftentimes become negative by their first birthday, even though they're born positive.
Oh.
And that's one of the problems with babies in this context, is that there's no way to prove the baby had it or didn't have it. So that's one of the questions. Is many babies can seroconvert, but not all. So the question is, did they have it? Did they not have it? Is there something magical about being a baby? Yeah.
So I have a friend, and he was born HIV positive.
Okay.
And he is now HIV negative.
You seroconverted. Okay.
Yeah, but that happened
Later.
in middle school age.
Yeah. So most of the studies out of Africa show it's usually within the first couple of years, but yeah, it could be later.
Okay.
And that's the big question: is how did that happen? No one knows.
What's the word you're saying, seroconversion?
Yeah, it's called seroconversion because sero is a fancy word to say like antibodies and stuff, serology. And so you go from being positive antibodies to negative. And so they seroconvert. Yeah, SERO. Or you go negative titer is a fancy way
Was
to
it
say
a false positive then?
That's what we don't know. And the hard part is that it's unethical to give babies HIV to see, if the test works, right? It's kind of a downer. But here's the magic question. Number 6. Why do people with AIDS have these wacky infections that none of the rest of you ever have?
They have a deficient immune system.
All right, they're immunocompromised. Okay, that's a word you're going to know, medical terminology, folks. Immunocompromised means what?
Helper T cells are
You-
unavailable.
That's right. You can't attack non-self. You want to, but you can't. So if I'm immunocompromised, I can't attack something that's an invader. Why can't you attack it? Why can't I attack?
Because it's being run by your helper T got exploded by all the little.
My helper T's went away. So let's go look at that picture one more time of the helper T's and what they do. So let me show you this picture here. It's kind of a general picture, but it works. So remember from our earlier group, helper T's turn on T's and B's, step 5 on, right? And then T's and B's do their job by killing things. So what does HIV do? It kills what? These are gone. So what do those two do?
Nothing.
Absolutely nothing, because you didn't give me the orders. You don't do anything in the army without orders. So if there's no orders, you don't do anything. So by killing off the helper T's, these two don't know what to do. So they don't do anything. That's why you get the infections your normal body would have fought off. Remember that Kaposi sarcoma? Right? That weird skin thing? No one gets that. But all of a sudden a bunch of people in San Francisco started getting it because your immune system should have fought it off. Theirs didn't, and that's what led to the discovery that this is something new. Right? If you have AIDS, athlete's foot will kill you because it will eat you alive. Because there's no way to stop it once it gets through your skin. Right? Make sense? Yeah.
Would you still have memory cells from previous infections?
But you can't turn them on.
Oh, okay.
So they wouldn't know that the thing is back. Right? So the helper system is there, but there's no one to call them up. Yeah.
How does the virus keep continuing the infection if it kills its host cells?
Eventually it wouldn't, but by let's try that again. By replicating so many cells so quickly, it doesn't need you to keep going. By the time your immune system's crashed, the virus is in billions of pieces. When you die, it dies, but it's already made its living by passing on to the next person. It's got to live long enough to get to the next person, and that doesn't care about you. Right? So AIDS is kind of peculiar in that it kills you slow enough, it's guaranteed to get to the next guy. Right? Yeah.
So the helper T's aren't secreting any interleukin, and so you're not. My question is, are you if the killer T's and B cells like bump up next to something that they're supposed to kill, are they going to do it, or there's
Nope.
just because there's no interleukin? There's
No one's telling me to kill you, so I guess you're okay. Because nothing would tell them to actually go out, clone, and start attacking. Right? You didn't get the order. Right? So let's go back to our case study here. Now you're all depressed. All right. So let's go down to question 7. Diagnostic test. At doctors, what do they look for to know about HIV in the body? They look for something.
T-cell count.
T-cell count or a CD4 count. right? They're checking your T cells. So tell me, if you had HIV, what would your T cells be doing if you had HIV?
It'd be low.
They'd be going down, right? They'd be dying off. So let's look at this graph.
Whoa.
The red line are your helper T cells, those CD4 cells, right? Over time, what are they doing? They're dying off. So as your helper T cells die off, there's fewer generals in the army. So there's fewer orders being given. Right? So a T cell count, or CD4 count. Right? Anyone guess what that blue line at the top, what a CD8 is? That's the cytotoxic T cells. Those are the ones that kill. They're fine. So a common misconception is you don't have an immune system. You have a complete immune system. It just doesn't get the orders to do anything. So those guys never hear the instructions from those other ones. You kill the general, so there's no one working. Right? But your T cell count, or your CD4 count, the more virus, the less T cells.
What's the a unit on the bottom? Of
They don't put a unit, but it could be months, it could be
Okay.
years, depending on when the virus kicks in.
Okay.
But normally this graph would be months after exposure, you crash.
So, sorry, the CD4 is the helper T cell, and
Yes.
the 8 is the cytotoxic.
Yes. So let's go back to our case study and fill that in. So what diagnostic test was it again? CD4 count, T cell count, watch your eyes. So T cell count. So if you know some of these, they say, oh, I made over 350 today. That's what they're talking about, the number of their T cells, their helper T cells. So if you have more virus, what will happen to the T cell count? It will
Go down.
go down. So if your T cell count is dropping, that means the virus is winning. If your T cell count's going up, that means the virus is less active, less metabolizing.
What's a normal count?
It's over 300. I have to get the actual number. I don't know what the actual normal value is. Usually somewhere between 3 and 200 is when they start getting concerned, and then that's when it drops down. So, a little bit of biology for 112. Retroviruses can't fix mistakes. So if you were to make a vaccine, tell me how that would work if the virus keeps changing. You can't make a vaccine, right? Can someone tell me why I would no longer have memory if the virus changes? It'll look different, right? So the concept of a vaccine is it has to be the same looking thing as the first time. The virus changes, it's going to look different every time I see it. Therefore, I won't remember it, right? To prove that I'm not making that up, but
So you're saying that HIV doesn't have a consistent code?
that's correct.
Oh, okay, that's not what I said.
Right. So retroviruses don't have an error check function, so when they convert over, they'll make mistakes and not care. They're going for speed.
Oh, okay.
So every time they make babies, they're
It
all
still
different.
functions the same.
Yeah.
It doesn't-
So in your cells, your DNA polymerase always checks that your cells are the same, but they don't. They're trying to race the clock. So they just crank out millions of copies. They're all different, potentially different. So they're trying to do it for speed, not for accuracy, right? So if we look at this picture here, no, you don't have to know this map, but this is the different kinds of HIV. These are called families. The different colors are different strains or groups. So they look different from one another. So let's say you had a vaccine for the US, you're type B. You decide to go to Brazil for the Olympics. That's not the same HIV. So your vaccine just quit working because that looks different than the one you got vaccinated for. So even if you could vaccinate, you'd have to change the vaccine depending on where you live and where you're going. Right? And then within countries, people can move and take vaccine viruses with them. Yeah.
So you could potentially be infected with all
Yes.
these types?
And people are. There are people running around who have multiple strains of HIV at one time, thereby cross-infecting everyone around them with a new strain. Yeah. Yeah, so notice these ones like this one here. That recombinant means those people got together and made a new one, right? Which is there. So you'd have to know what version you're getting to make the vaccine that would work for that version, and it wouldn't work in the next country over. LA's HIV is different than Seattle's. So within a country, they can vary. right? Because they're all different. So every time you got a new color, you'd have to relearn what that is. Right? So worthless trivia, that's how they work out now. Right? So you have two main strains. They mentioned HIV-1. Right? They're in groups, they're in subgroups, and within those are subclasses. It's like software. There's like A.1.A, you know, and it keeps going down. And they ran out of letters after K. Right?
And it's just going to continue to grow over time.
As more and more people get affected, there's more variation in the system. Make sense? Yeah.
Isn't there different strains of flu?
Yes.
How do they vaccinate for that and have it?
They don't. That's why they guess.
They guess.
They guess.
That's why you get a new flu vaccine.
Right. That's why you have to get revaccinated every year, because they don't know what strain you have.
I mean, could they do something like that with
They could.
HIV?
The problem with HIV is, for the public health thing, is you give someone a vaccine in the US, they think they're immune forever, so they're going to travel and do something stupid, and they don't realize it doesn't work there. So the fear is you'll just get more HIV as people think they're immortal, instead of realizing it only works in this town with you, not the next state over, not the next country. So one of the concerns of public health is people would falsely assume that it works everywhere like measles does. Measles is the same everywhere, right? But HIV is not. Flu, just, you do it every year because people know to do it every year. But you know, a lot of people don't believe in vaccines. Witness Portland, right? So you got that problem too, right? Make sense?
So even for people like healthcare providers, they don't do.
Right, so you'd have to know where you're going and what strain is there, but the people you meet could be recombinant anyway.
Right. And it's not feasible to, like, you know, if you're like a traveling doctor, like, could you just get all of them?
No, not really, because even if they gave that to you, there's no guarantee that's the one you're going to have. So they're going to end up taking the drugs anyway after exposure, which then why get vaccinated? It won't actually achieve what you want to achieve. Right? Make sense? So once you change a virus, the memory has to reset every time. Understand that? Make sense? All right, so let's go back to our case study. So we're going to do a little hypothesis testing here after we look at where we can stop HIV. So look at your diagram. Look at those steps. Someone give me a step number on your diagram where I could maybe prevent, stop HIV.
2.
Okay, 2 might work. Can you think of one maybe a little better than 2?
1.
4.
How about 1? All right. Imagine if you never got exposure. Wow! If no virus enters me, I don't have to worry about the other steps, right? So no exposure would be, that's the whole condom thing, right? Let's assume you got exposed. Name another step that you could maybe do something with. Now say number 2. Now 2. We'll get to 4 in a minute. What would happen if you have changed antigens on the helper T cell? That's right. The HIV would not see the cell if those antigens were changed. So if you had different antigens on your helper T, the virus wouldn't know that's you. If you read step 2, it's looking for a shape. So how do you change your antigens? Go back to the question on the prior page. Where do antigens come from? Proteins. Where do proteins come from?
DNA.
DNA. So how do you change your DNA? You don't. It's called genetic immunity. You're born with it. So some of you are immune to HIV. Unless I give you HIV and check, there's no way to be sure. Anyone want to volunteer for that experiment? Probably not. So there are people in this world who will never get HIV because their receptors, their antigens are a different shape. HIV doesn't know who they are. Okay? But they had step 1, they were exposed, but the virus can't find the cells to infect. Yes?
Isn't that for specific, because you were talking about how HIV is
Yes.
in North America, it's a specific HIV, so you can only be immune to.
Correct. That's one thing. We don't know if you're immune to everything or just the ones that you're exposed to. All right? So there are people who have genetic immunity. Right? So let's say that didn't work. What's the next pathway you could possibly stop HIV? Now say step number 4. As they mentioned in their presentation, we can block that enzyme. look at step 4, the virus has to use an enzyme to convert itself. So if I block the enzyme, there's no DNA formed. No DNA formed. So Truvada, AZT was in that group. That was an AZT drug, Z class. They're all trying to stop step 4. So you were infected, it got in your cell, but it can't find your DNA. It can't get in your DNA. Make sense? Find another step you could stop. Go down near the bottom. Past number 7.
8.
Hey! Step number 8, 9, and 10. Read steps 8, 9, and 10 and tell me what the virus is doing.
It's maturing.
It's growing up, it's maturing. How's it doing that?
Processing proteins.
It is, and isn't there some kind of enzyme listed in there? Something with an ACE?
Protease.
Protease. And what can we do with enzymes? We can block them, right? A la 112. So we can block the enzyme in those steps. The protease enzymes. They call these the cocktail drugs. So if you know someone taking a protease inhibitor cocktail, they're stopping step 8, 9, and 10. The virus can't grow up, a la Peter Pan. So don't get exposed. You could have genetic differences that prevent from getting in. You can stop it from finding your DNA and stop it from making babies. Those are the only known ways to deal with HIV. Yes?
Could you do it number 5?
They're currently working on that. I heard that Merck has a drug potentially for stopping step 5, but currently there's nothing on the market for step 5. So if you get a needle stick at the hospital, they're probably going to give you drugs for step 4 and step 8, 9, 10. We're going to block it from getting in and block it from coming out. Therefore, you can't have new infections because you already broke number 1. And we don't know if number 2 works. So they'll give you those. Yes?
How long would you have to be on the medications?
It varies. Do you remember from Truvada how long I have to be on it for the post-exposure? Is it 6 months? Year?
I honestly can't remember.
I don't remember. Yes.
A lot of like EMS policies will test you every month or so for a year. And then if it doesn't show up, they stop sticking you.
Yeah, because that's the whole 3-6 month thing. So I have to wait 6 months to see if it activated. So that's the idea. So yeah, if you get a needle stick or whatever, they're going to give you these drugs prophylactically until they think the HIV is clear of the system. Yeah.
So if you blocked the enzyme for long enough,
Yes.
I mean, would it be, like, how long would the intact DNA cell live for? Like, would it be possible to keep blocking it until the cell just, like, died, or is that's not how it works?
So this one? So in theory, if you kept doing this, the virus would never change your DNA, so the cell would live forever because it only dies in 8, 9, 10.
Okay.
So you'd never lose your helper Ts if you could do step 4 continuously. Yeah, if you block step 4. Yeah.
This might be a silly question, but does the helper T cell, does it become an APC? Like, would it be possible to give an interim?
It actually doesn't become an APC.
Okay.
But the other cells, when the HIV is in your bloodstream, the other cells can eat it and present the APC. So there are other cells announcing it. You're just killing the one guy who can order everyone else to do something with it. So you okay on those steps? So those are the current understanding of how to prevent it. So look at question B. You and your team have a minute or so. You're going to do some hypotheses. You can guess where it's the worst, how they got it, and then how risky these different behaviors are. I'll tell you